All right. All right. Well, hello, everyone. Thank you for coming today to this training in the NICS seminar series. Today, we're going to be talking about HPC and engineering. My name is Vince Betro, and I work here at NICS. I also happen to have a PhD in computational fluid dynamics. As a consequence, I've done some HPC and engineering, and there are lots of other areas other than just obviously CFD. So today, I really just want to give you a good overview as to some of the interesting things that are going on with HPC in the engineering world. It's not an exhaustive list, but hopefully it'll inspire you to go out and look and see where you folks that are just now starting on your engineering road really can look to update your skills and make sure you have the right sort of programming skills, the right sort of data analytics skills to be able to deal with some of the modern problems that you'll run into in engineering optimization and performance. So again, I'm going to talk a little bit about why in the world we would use HPC. I'm going to discuss some of the things that we solve with HPC and how we do it. Why is HPC necessary? I mean, obviously folks have been using paper and pencil or their desktops for a long time. Why are we suddenly in a situation where HPC has become necessary? And I'm going to discuss some common codes. So without further ado, I also want to thank the Sim Center at the University of Tennessee at Chattanooga for a lot of the graphics and the videos in this presentation. They were an excellent source of material. Thank you. So why use simulation? Okay, well, for starters, we want to determine viability before we build expensive prototypes. Obviously, some of the most expensive things that we do in engineering are these wonderful, and this leads well to the next topic, this sort of test, break, rebuild, break sort of experiments. And those work really well, except for the fact that, you know, if you're trying to have a prototype of a fighter jet or a ship or some sort of land vehicle that costs, you know, hundreds of thousands of dollars just to build the prototype, you don't want to have to be constantly crashing it and testing it until eventually it works. I'd like to figure out, you know, even if it's just narrowed down to 3 or 4 possible designs on the computer, you've saved yourself an incredible amount of error-prone and expensive testing. So you can break it down to just a few that you have a good chance of working, and then you can figure out which one is the best based on actual performance in the real world. You know, we had when I was at the Sim Center, we had a small mock-up of an F-111A, and that had been used in a wind tunnel at Arnold Engineering Development Center. This little tiny model was, you know, maybe so big, and it cost tens of thousands of dollars to build because it had to be machined to a perfect precision. Similarly, anytime a change had to be made in the model, that would cost thousands more to have it go back to the machinist and have part of it rebuilt. So this is something that we were able to very quickly do using CAD. Create an exact model, exact replica of the plane. There are now these things, 3D scanners that you can use. Put stuff directly into CAD, and you're able to get a very exacting model and perform tests on it in a computational environment. The other thing about this that's interesting is once you get down to being able to do some testing, you can do some optimization. I mean, such things as the adjoint method, and if they're linked up with proper CAD hooks where you can actually, you know, you're not asking for a change in the location of a certain element below the precision of machining tolerances. So you've got to be cautious of that. But as long as you stay within those levels of precision where it's real world machinable, you can optimize lift, drag for a wing. You can optimize the aerodynamic forces that are causing drag on trucks or cars. There's lots and lots of different options that you can use simply by having a computational model to work with. All right, so here's an interesting example of an engineering problem here. We are interested in modeling human behavior. Okay, now that's not your traditional problem like I was just talking about, is it? It's not we have an airplane or a car and we want to change the way it's designed. This is a situation where we actually want to look at human behavior, and we're interested in maybe how humans and sorts of things like traffic react when a certain instance occurs. And so we're going to actually have an example of that later on, where we look at how folks deal with evacuation from both the cars on a road perspective as well as the people being people perspective. And that actually is very important when you're looking at these problems and trying to make sure that you stick to reality. A lot of these tools will run on a desktop, but they take days and weeks to run. So if I'm in a situation where I'm a first responder and there has been a catastrophe, I would like them to be able to model that catastrophe much more rapidly than days or weeks, so that I can get some useful information like which roads should I close, how should I evacuate people most effectively. And that's where real time is very important. So not only have the problems grown larger and more complex that we're interested in, but the desire for real-time predictive analysis has pushed the envelope to where HPC is truly necessary. Uh-oh. You're kidding me. How do I get rid of this?
Try
There we go. Yeah, it's like it, so just give me back to Finder and I'll do a force quit. Sorry, everybody. I apologize. We had a little issue with PowerPoint locking up, so I'm going back to reopen that, and I will be back to sharing in just one moment. I very much apologize for that being difficult. Okay, so we're going to try something a little different here in hopes that we don't run into that same issue. Okay, I think one of the issues may have been the attempt at loading some of these videos, so we're going to go for the in-window editing version view. So as we were saying, some of the things that are interesting are not just traditional sort of things like fluid dynamics, things like the physics of solid mechanics, stuff like that we have nice, wonderful equations that we've gotten pretty good exact science and modeling. We're also interested in things that are more stochastic, like human behavior. This is an example of a simulation where we're looking at a city where a contaminant has been released. It could be a train with hazardous waste on it or some sort of hazardous material that's derailed. It could be an actual attack. It could be several things. But what you're interested in is twofold. One, you want to see where that is going to go, right? Cities have these sort of urban canyons. If you've ever been in a large city and walked down a street, you know how much windier it is down at the street level than it is if you're out in the middle of a park because of those urban canyons. So using sort of a viscous model where you look at the surface of the earth as the viscous surface, and then you look at these large discretizations, say a meter by a meter, 100 meters by 100 meters, you're able to actually do atmospheric boundary layer calculations and figure out pretty much exactly where that is going to go given the geometry that it has to work around. So that's cool. But now we're not just interested in that. We're also wanting to couple that simulation with the fact that you want to see what people are going to do. Now, we don't have nice, pretty equations that say this is what people are going to do. What we do have are stochastic models, and we have statistical information that says, okay, 1 in 10 people is going to ignore what you tell them and try to go an alternate way. 1 out of 20 people is going to ignore a shelter-in-place directive, and they're going to happily turn around and try to flee. So there's all these different things that may happen, and so what the first responders need to be able to do is know what streets to close, what routes to get people on, based on where the majority of people live, what are the most trafficked routes, and based on the fact that no matter how hard we try, not everyone is going to cooperate, okay? So this next thing, we're going to take a look here, assuming I can get it to play. It doesn't break. Oh, bummer. Don't send. Gotta love PowerPoint. All right. Try that again here. Oh, PowerPoint. What am I going to do with you? All right. So here's what I'm going to do. I have this fear that PowerPoint is going to be incredibly difficult to work with today. So given that, I'm going to try this one more time. Oh, yeah, that was pointless. All right, I'm going to pull up the PDF of this, and I have these videos separately. So we're going to use the PDF version, and then we're going to go through the videos on their own. So my apologies, folks. Sometimes technology, as they change versions of things, doesn't keep up with itself very well. So anyways, so just as a still picture while I go and go looking for these videos, what we're interested in here is, again, not just what's going to happen with the material, we're also interested in what's going to happen with the what's happening with the people. So if you look at this image, what you have here are these little dots, and these are agents in this agent-based statistical model. And each of those agents has a place of residence. They have kids, they have a certain work schedule, they work at specific places, and they have these sort of statistical abilities to be someone who does or doesn't follow directions. When you take that model and you're able to tweak those parameters as you go through, try to get it to be as close to statistical reality based on what we know from science as possible, you're actually going to be able to see the people that are able to make it out, the people that are paying, that are stuck in a traffic jam, the people that are obeying, the people that are disobeying. So let me, very quickly, bam, sweet. All right, so I'm going to play this video here. There we go. All right, so you take a look at that. And again, as you see here, what you have are all these agents. These agents have very specific traits. The agents that are in red are agents that are going into the danger zone. Those that are in purple, blue, and green are trying to leave the danger zone. Those in blue are in gridlock, which, as you can see, is getting worse and worse and worse. And of course, as all those people that are leaving get in their cars and try to get on the roads, that gridlock will only become worse. So what you can do as an engineer here is you can look at what street should I close? What thoroughfares are causing the most trouble? What routes, given the spread of this contaminant, are people best off taking? And that's very important, because you don't want to, even if it's the quickest, easiest route, if that's the next place this contaminant is going to spread, you don't want to send people into the cloud, right? So, and then as you can see, as we get deeper and deeper in, there's just this festering of folks in the middle. They just can't get out. There's no way. And that is where we tune parameters to try to look at what we can do to make that not happen, because that's obviously that sort of gridlock is the kind of thing that takes a tragedy and turns it into a colossal tragedy. Excellent. So, example of engineering problems. Here's another sort of more common type of engineering problem that's not quite so mixture of CFD and stochastic modeling. So we want to model fluid flow, right? That's something that people do to optimize designs. It's something that people do to look at things like pipes. And all sorts of different situations. You know, you want to look at where the lava is going to go next. If you're in Hawaii and you're trying to save a town and you didn't know where to divert it, if you can, this is the sort of modeling you'd use. All right. So in this particular case, you can do turbulence modeling or not. Obviously, we know that turbulence is real, but we can get an amazingly good picture of things even without turbulence modeling. Same with viscosity. Every fluid has viscosity, which means it sticks to the wall, and slowly but surely as you move away from the wall, gets up to free stream velocity. Okay. Here we're going to discuss the 2D Euler equations. All right. In 3D, it works about the same, but 2D makes it a little easier just to kind of figure out what's going on. And obviously, the more complex the phenomena, the more fine the discretization has to be. In other words, when you discretize something, that means you're looking at little tiny pieces and in order to find a trend overall. So for instance, if you have integration, real simple integral of just a simple function, and you do your real Riemann sums where you make the little boxes, add up the sums of the delta x times the value of the function for each of those boxes, you get a pretty close approximation of the integral. Similarly, if you take those boxes and you make them smaller and smaller and smaller, you get an even better approximation of the integral. This is that situation. The smaller we make our boxes, the smaller we make our elements, the more data we have at a fine grain, the better job we can do modeling something. That should give you another good hint why we need HPC in engineering. We want to be as fine and discretized as possible. Okay, so here's an example of using those equations to model the flow across an aircraft. All right, so this guy has all these nifty little vortices that are being shed, right? Little turbulent vortices. What of them? Is it just a cool picture? Does it make us happy just to look at it? Well, yeah, if you're me, it does. But more importantly, it tells us something about the flight characteristics of this airplane. What we can see is we have these two areas of turbulence, which is an area of low pressure, okay? And it's on top of the wing. Well, last time I checked, that's a good thing, right? For lift, you want the pressure to be high below the wing and low on top of the wing. If for some reason this was to be reversed at a certain speed, we'd want to know about that because the pilot is not going to want to go that speed. All right. If suddenly when he goes from Mach 1 to Mach 1.5, the plane decides it wants to drop out of the sky, that's not an acceptable design. And so these are the ways that we can tell what will and won't work pretty much right off the bat before we have to go making these incredibly expensive models. Now, this is not just about planes, trains, and automobiles, okay? I know there's a lot of that I'll discuss because it's very relevant in our society, but this is also about environmental modeling, okay? Again, we're talking about atmospheric boundary layer. We can look at the Earth as if we were looking at a ball in a tank of fluid, okay? Because the Earth is effectively that. And even though there's no fluid outside of the atmosphere, okay, at that level of the atmosphere, we still have enough fluid we can look at how it flows around this ball we call Earth, and viscosity-wise, what's going to happen. So this is an example here. We're looking at the Smoky Mountain National Park, and that's here in Tennessee. It is America's most visited national park, and as a consequence, it's also America's most polluted national park because of all the car traffic. On top of that, the reason the Smoky Mountains are called the Smoky Mountains is they're prone to temperature inversion. And as a consequence, all that smog, all that exhaust fumes that we release when we're driving through like to kind of sit and stifle right behind these ridges. And so based on this sort of analysis, we can look at some of the worst stifle points for that matter. And let's say somebody was wanting to build an old folks home in the Smokies, which is, there are lots of them. It's a great spot to be. It's a beautiful place to look at every morning, but you don't want to build it right in the middle of one of the spots where the air quality is going to be the poorest. So these are sorts of, and then of course you can look at where you want to build roads so that you don't contribute to that air quality being even more poor, or even poorer, excuse me. All right, for the sake of time, I'm going to skip over this one and we'll come back to it. Again, this equation here is not something that should make you run away now. Please don't run away, okay? The point is that of showing you this is all we're doing is we're modeling partial differential equations, okay? In this case, it's a partial differential equation. We're looking at it in an integral form. And so effectively, we're integrating these fluxes over these faces to find out what sort of changes, what flux we can expect. Because if you're at all familiar with fluid modeling, it's a control volume approach. You look at one spot, you look to see what changes in that fixed viewpoint to determine how the fluid is actually behaving. Okay? Again, when we talk about discretization, hopefully this picture helps you a little bit. We're often talking about a mesh, okay? That's not always the case, but in most cases, we're talking about a mesh. A mesh says we have data at each one of these mesh points, okay? And from that data, based on our decision as to how we want to extrapolate, we can look at saying, oh, if we have data at those 2 points, then we also know what that data does along this edge. And once we know all that information, we have discretized the problem. We effectively have what would be tantamount to having billions of little sensors taking readings all around the area and then communicating with each other to determine what is happening in between those, any group of 2 sensors and how things are changing as we go along. All right. So again, you're going, okay, cool. You have integrals. Okay. You're discretizing those integrals. Okay. But those don't look like little Riemann sum boxes. So what do you mean? Well, we have to take that using our friend Green's theorem and Taylor series expansion. We turn that integral problem or the integral differential equation into a linear system of equations. And what do we know that computers are really wicked fast at? Solving systems of linear equations, okay? Once we've linearized the problem, now what we have is just a big matrix and two big vectors, and we just need to figure out what goes in, if we're solving ax equals b, we need to figure out x. And computers are really good at that, okay? So in 2D, you can see that the system is n by n, all right? Number of nodes by number of nodes. And in 3D, it's n by n by n, all right? So that means we're going to end up with huge, huge, huge matrices. Again, computers are good at those, but we can use things like compressed row storage to deal with these sparse matrices, or special solvers to deal with these sparse matrices, in order that we can actually come up with a solution to these giant things that may even be too big to fit on a computer, more or less multiple computers, okay? So again, if we're going to do this on a real geometry or with real data, with a real fine grain, we're going to have to use HPC. And we're talking about things where if you have a 100-node mesh, you've got 10,000 entries in that matrix. If you've got a 1,000,000-node mesh, right, you have a trillion entries. If you have a 1,000,000-node 3D mesh, oh, Katie bar the door, you've got a quintillion, okay, entries. That's huge. Each one of those entries takes up bytes, and you only have so many bytes, right? So if you have double precision, those are 8-byte numbers, 8 times a quadrillion, and suddenly you're way past tera, you're way past giga, you're way past exa, okay? You just have to have more memory than that. So you need to go way past even the biggest shared memory machine into a distributed memory machine where each computer takes a little part of the problem and works on it. They talk to each other and they come back and they keep iteratively working through to the solution. All right, so in the following slides are 2 issues not found in experiment that we could have detected just by running lots and lots of flow simulations, okay? in order to be completely diligent about this design. All right, so this particular situation here is this is a submarine, obviously, and those of you that aren't familiar with the concept of cavitation, cavitation is basically when you have these wonderful little turbulent eddies forming, and they cause a low pressure field between the metal of the propeller and the rest of the fluid around it. And so effectively, all of particles of fluid become little tiny meteorites almost that just ding away at the metal. If you've ever looked at a boat prop that's had its day, you'll see all these little tiny dings in it, and that's from cavitation. So the problem they were experiencing here is they put this bird in the water and tried to do an emergency propeller reversal, where they've got to very immediately go from forward to reverse. And in doing so, it goes through a couple of stages of RPM development where it actually causes it to break. The cavitation gets so severe that the pressure can't be withstood by the material. And so redesigning that prop so that those specific spots don't happen was crucial to being able to do this, necessary maneuver, right? If you're heading forward something and it's not good news, you want to be able to back up, right? Another situation was this is an Osprey aircraft, all right? This was an aircraft used by the Marine Corps, and the first time they took it up in the air, it came crashing back down, and several Marines lost their lives. And so the question was, why? What happened? Well, as it turns out, at a very specific RPM, you end up with these wonderful little vortices that are going in opposite directions. So you have high pressure above and then high pressure below, depending on which side of which side of the aircraft you are on. And so what ends up happening is it spins it around, can no longer generate lift, and it falls out of the sky. So by going through and running all these simulations and finding that one bad spot, they're able to deal with this by making sure that the propellers go at different RPMs, just so that they can skip over that bad spot, redesign. There's lots of different things that they took into account so that would no longer happen again. All right. Another cool thing about engineering and HPC and engineering is that we can visualize things that we normally can't see. All right. So let's do that. So in that situation, we may have E&M phenomena, okay, electromagnetic phenomena. So we can't see that. We can see the results of that in physical experiments, but it takes a lot of equipment. What's really neat is being able to look at how, radio frequency scatters off of different objects and different materials types, so that you know how to make your best antenna, how to make the antenna that's going to capture the most signal. So here's an example of using Maxwell's equations, and we're looking at an antenna. Right now, I know it looks like a circle, but imagine that's a cross section of an antenna. It's an infinitely long cylinder, okay, or what is effectively an infinitely long cylinder. The length is much greater than the diameter. All right, so you're looking at how that occurs when you have a situation where you're scattering these different types of electric fields. So you can better design things to keep interference down, keep noise down. All right, so here would be a video of some waves in a box, and I'll play that for you now. There you go. So this is actually a simulation. There was an oscilloscope that was, an oscilloscope combined with another device that they were using. You have to forgive me, I don't remember what it's called, but there was a little box, and they would pass these waves through this box, and this device would measure things like amplitude and period and all that. Then they turned around and were able to simulate and get the exact same answers as this, several $100,000 piece of equipment did. Once you get to the point where you feel confident in your simulation, that's when you can start to really design things with it. All right, so optimizing current designs. There are some things that we do that we need to do better. Energy is a hot topic, and the reason it's a hot topic is it's finite, okay? Even with things like renewable energies, The more people, the more demand. Eventually, there are things that are going to constrain that problem. Even if you can keep renewing the energy, you can't put more solar panels than there is surface area that's getting sun. Okay, for instance. So we have to do a better job with our energy. And one of the things that we can do with our energy is we can look at things that are bottlenecks, hot spots, maybe you want to call them, in energy use. All right, trucks are a huge hotspot for energy use. All right, they are something that is part of our society and trade structure that's ingrained, and yet they are incredibly fuel inefficient. And so that is not only bad for the environment, but it costs everyone more money because you've got to pay even more for the trucks to deliver these goods. It just continues to fall down the chain as to who has to sort of pay for this expense. And so one of the things we can do is we can look at one of the most expensive parts of trucking, which is the fuel, and see if we can lessen the amount of fuel that's necessary. So using the Navier-Stokes equations and some turbulence modeling, we were able to look at all different configurations of different trucks and see where the worst spots were for this sort of fuel sucking. Okay, and on top of that, we were able to go back and we were able to look at several different solutions and find out which one did the best job of sort of mitigating this drag that was being caused. All right, so here's the truck. This is what I mean when I talk about a truck, a semi-truck. Okay, and there are two spots where really bad things happen. One's right here in this gap, and the other one is right over here in the back. Excuse me, three, and the third one is underneath it. Okay. Things you don't want. You don't want low pressure fields there. Why might you not want a low pressure field there? Well, if you have low pressure behind the cab or under the body or behind the base, it's effectively acting like a vacuum. It's sucking the truck backwards. That is drag, okay? Drag is not just the pushing of fluid, air in this case, on the front of the truck. And it's not just the friction on the street, but it's actually creating a whole other sort of suction separation zone that is actually causing excessive drag on the truck. If you've ever driven by a truck and kind of almost gotten sucked in one way or the other, that's what we're talking about. We're talking about those vortices that are being shed that are causing areas of low pressure that are not optimal. So as you can see here is a great example of this sort of drag that's happening behind a truck. Okay, all these little spaghetti strands are streamlines of a particle, and you can see that they go from being nice and laminar to being very turbulent behind the truck, which of course means that you have drag. Okay, now if they're able to use half mud flaps, okay, suddenly that drag isn't nearly as bad. If they use some special slatted mud flaps, the drag is even less appreciable. And if you can knock out that drag, what you've effectively done is you've raised the lift, or in this case, the push, okay? Which means you have to use less gasoline. They actually guesstimated about 8.6% less gasoline. Let me go ahead and pull up this video here. And as it turned out, the company actually was able to see almost a 10% reduction in their gasoline needs. This is a company called U.S. Express Trucking out of Chattanooga. And by doing these simple retrofits to trucks, which literally cost on the order of $200 a truck, okay? And let's say $200 a truck times 200 trucks, all right? So that's $40,000. It doesn't seem like a minor amount of money, like $40,000. But you have to remember that this particular company, its fuel bills every month are about $5 million. So 10% off of that is 500 grand. That means in a month, they've paid it off tenfold. Okay, so this is the sort of situation where a very small change, a very small addition, infusion of money to change this design can make a large impact. And without engineering, without high performance computing to generate these results, they might still be trying to figure out what the best way to fix that problem was. Okay, getting near the end here, folks. All right, so another option, energy-based again, chemical reactivity, right? So if you're not familiar with a fuel cell, what a fuel cell does is it takes hydrogen gas and oxygen gas, it combines them in a chemical reaction, which leaves us with electricity and water. Right? So it is like nature's perfect energy source. It is, the only problem with it is this: there's free oxygen, right? I mean, we're all breathing. There's no free hydrogen, and that's probably for the best, because free hydrogen would mean every time we lit something, the whole world would blow up like the Hindenburg. So that's no good. So what they've done is they've used methane, CH4, which is actually, very readily available. Every time a cow goes potty, we get more methane. Okay, it's the nature of decomposing. It comes from that, and an oxygen, and what's left over is water and some carbon. Okay. So they use these two things, they put them in a fuel cell, and this reaction occurs, creating electricity and water, and everybody's happy and wonderful. The problem is that it's difficult to get as much direct use, even though the outcome is cleaner than burning this methane or this natural gas. It's difficult to get it as much efficiency per amount of natural gas through a fuel cell as it is just by burning it. So what we've done in order to rectify that is to go back and redesign the channels in this fuel cell to make that reaction more efficient. If we can make that reaction more efficient, then what we end up with is more energy for less methane, and suddenly all of a sudden that issue with not being able to get as much energy per methane from a fuel cell gets turned on its head. All right, so here's what a fuel cell looks like. It's real simple. It's just a bunch of channels through a material, okay, that is set up to chemically react with those two things, hydrogen and oxygen. All right, so initially, before they did some adjoint-based methods to reshape this, if you notice here, you have you have the natural gas flowing in, and it's reacting with the oxygen, mostly at the ends of each of these little channels. And then, of course, there's leftovers flowing out. That's not so great. It means you're not getting optimal coverage. You're not getting an optimal chemical reaction. It's all about surface area. So in order to fix that, they reshaped the channels ever so slightly. And as you can see now, all of a sudden, bam, 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 it's flowing down through every channel, and you're not getting this egregious waste of outflow. Okay, structural dynamics. We would like to be able to test blast-worthiness of things without bombing them. That's, again, the ultimate destructive testing. We want to be able to simulate earthquakes and see what's going to happen to the buildings. We want to know what might happen so that we can most effectively evacuate folks. Now, obviously, we don't want to just try that out. If you were running for mayor of your town and said, well, we're going to blow this up and see what happens, you're not going to get elected. But if you can try it out on a computer first and get a good idea, then you're in a better situation if something like that actually does happen. All right, so everything down to COMSOL and SolidWorks. Right, these are desktop resources, and you can do small designs like bridges on them, and you can actually test them using the linear elastic equations to see how structurally sound they are, see how their factor of safety stack up. Having said that, if you want to do a real one of these, a real bridge, you have to farm it out to multiple computers. And again, high performance computing comes in. Okay. Codes running at NICS. So we have lots of these different commercial packages like COMSOL, ANSYS, that perform engineering simulations. Most of the time they're on a desktop or on one large memory node because they're not set up to distribute very well. However, things like OpenFOAM and SU2 out of Stanford are, as well as NASA's Fun3D, those things are set up to distribute very well over multiple nodes. And so they are able to handle very, very large problems, very, very large simulations. Right? Sometimes the package will generate your discretization for you. Sometimes you have to generate yourself. But obviously, the better job you do of discretizing it and then load balancing, the better job that the better results you're going to get, and the more rapid results you're going to get. And so here's some CFD codes that we work on at NICS. So I call this a tale of two CFD codes. Sorry. Just want to make sure I was almost done here. All right. So one of the things that we worked with was an excellent code out of Texas A&M, put together by Professor Diego Donzis, called DNS, right, Direct Numeric Simulation. This was an amazingly adept code, has a very wide set of parameters that it works well on, and it can do lots of different kinds of simulations. The problem was it just wouldn't scale up. And simply by using a different I/O scheme, right, where we were, instead of everybody trying to read from one place and having to stand in line, we took the file and split it up into multiple locations and let everybody, a few people go off to each of those locations in order to read that file. Suddenly the code got knocked down by like, almost half, definitely by over a third in execution time, making it possible to actually get some of these really large runs done in a reasonable amount of time to where you could actually run it on one of these public supercomputers. I mean, there are wall time limits. You don't necessarily get 7 days to take up the entire Titan machine at ORNL. You have a certain amount of time that you're allowed to use it. So another good example is working with FOSTA at the University at Texas Tech. All these different optimizations were tried out, and yet at the end product, memory bandwidth was what slowed it down. The ability for the memory to get information to the processor in a timely fashion. And so the best way to do that was just to spread it out over more processors. So there was less contention for that memory channel between the processor and RAM. These codes use these very high-powered functions like LPACK and BLAS. These were, started here at UT with Jack Dongara's Innovative Computing Laboratory, and they're pretty much ubiquitous at this point. You definitely want to use things like LPACK and BLAS or their accelerator counterparts like Magma in order to accelerate your code. There's no sense in you writing a brand new algorithm to solve a matrix that somebody's already optimized. All right, so a couple of pictures just to drive it home. This is droplet-laden isotropic turbulence, where we're looking at a particle model. These are great because they vectorize well, because the particles are somewhat independent of each other. They don't follow a specific grid pattern effectively. This problem required a minimum resolution of 1024 to the third data points, okay? So a minimum resolution of a trillion, minimum, right? That's a lot. So if you actually want to be able to functionally have a trillion, 8-byte numbers somewhere on one computer, good luck. But if you want to do it on several computers, you're in business. All right, and last but not least, one of the neat things, again, this is where all these fields kind of come together. Here's the use of engineering of CFD in looking at modeling blood flow, okay? So you're looking at blood flow through the lungs in order to be able to determine spots where it maybe is constricted, where a stent might be helpful. If you have such a stent, will it actually hold up to the rigors of being in the lungs? All these different things you can test out before you ever even have to move over to a human subject. And that's really the goal here, is to save money, time, and human life, not in that order. Actually, quite probably in the opposite order, okay? So this is me. Please feel free to write me an email if you've got any questions about anything I've said, or you want more information about something. I'm very happy to pass that around. This presentation will be listed online with all the other next seminar series presentations, and hopefully this wet your whistle a little bit for what sorts of things you as an engineer can do in high performance computing. And like I said, make sure you go out there and get some good training in programming, and you'll be a shoo-in to be able to take care of whatever you need to in the engineering of the future. So with that, I say thank you and open the floor for a couple minutes of questions.